Sometimes a direct proof feels a little bit tricky, but there's a way to do it in a different direction that helps us out. So, what do I mean by this? This brings us to proof by contrapositive. Here's a theorem, another math theorem. For any integer n, if n squared is even, then n itself is also even. If n squared is even, then n is also even. So if we were to write this out in logical symbols, for all n in Z, E of n squared implies E of n. Now, I'm not going to go through an entire attempt to prove this directly. I just want to highlight that it's not really obvious how you would do this proof, the proof that shows this arrow that if n squared is even, then n is even. If I went and used the definition, for example, I would say, okay, I know that n squared, there exists a k in the integers such that n squared is equal to 2 times k. Okay, so that's great, but what am I going to do with this? I can try to do something like say, oh, well, therefore n is equal to the square root of 2 times k, but now I have a square root, and that seems really challenging for me. I don't know how to do square root manipulations yet in terms of showing that things are even or odd. This seems like a dead end. I'm not going to do well. I'm not going to write a satisfying proof this way. Now, it turns out I can avoid often going in that direction by doing a proof by contrapositive. And a proof by contrapositive relies on the idea that if I am doing a proof that P implies Q, well, guess what? That's logically equivalent to the statement not Q implies not P. So this is the idea of proof by contrapositive. Instead of proving that P implies Q, I'm instead going to prove that not Q implies not P. So instead of proving my original statement for all integers n squared being even implies that n is even, what I'm going to instead prove is the contrapositive, which says for all integers n, not E of n is not even, implies not E of n squared. N squared is also not even. So this is the contrapositive. And indeed, the opposite of even is odd. And so another way for me to say this would be for all n in the integers Z, O of n. So let's assume that that's a predicate that means n is odd, implies O of n squared. So now I am in business. I can write a proof that's going to go a lot better for me. So in order to do my proof, I'm going to work in much the same way as before. I'm going to start with what's now my premise. So originally talking something about n was my conclusion, but now it's become my premise. So what I'm going to do is start with my premise. Let n be odd. And I'm going to write in my conclusion. Therefore, n squared is odd. Now I need to use my definitions, just like before, we're working outside in. So by definition, if n is odd, then there exists a k in the integers such that n equals 2k plus 1. We know that. And we want to show, so our definition of the conclusion, which I'll write right above, is that there exists a j in the integers such that n squared is equal to 2 times j plus 1. So let's see if we can connect these two pieces. I'm going to try to go from the definition of my premise down to the definition of my conclusion. So I'm going to go right below my premise, and I'm going to ask myself, what do I know about n squared? Well, if I say, okay, n squared, I can plug in this 2k plus 1 because I've assumed in my premise there is a k such that n is equal to 2k plus 1. So I can plug that in if I want to. N squared is equal to 2k plus 1 squared, which from algebra class, okay, 2k plus 1 squared is equal to 4k squared plus 4k plus 1 by the FOIL method or whatever method they're teaching y'all to square things these days. Okay, so now I have a formula for n squared in terms of k. What I'll do now is I'll say, okay, let j be equal to the quantity 2k squared plus 2k. This is allowed. I haven't actually done any math in this line. I've just given a variable named j to some quantity, 2k squared plus 1, that I already have defined. And what I'll notice now is that then n squared, because of the clever way I've chosen j, n squared is equal to 2 times j plus 1. Because here I'm going to get 4k squared when I multiply 2k squared times 2. I'm going to get 4k when I multiply 2k times 2. And I'm going to add the 1 at the end. And now I am done. Because again, I needed to show that there was such a j. I constructed it. I made it out of the variables that I had already defined. I constructed it, and I show that n squared is equal to 2 times j plus 1. I've filled in my proof. I have shown the contrapositive. If n is odd, then n squared is also odd. This means that that's actually enough to prove the theorem. My original theorem was that if n squared is even, then n is also even. I proved the contrapositive. The contrapositive is logically equivalent to the original, and so I am done.